Good morning, good afternoon, good evening all. So ladies and gentlemen, welcome to one of our first technical session of the Congress dealing with binder performance and testing. I will briefly introduce myself. My name is Frederick Delphos, working for ExxonMobil, and I had the honor to be the former president of Eurobitume from April 2020 until end of April 2021. I was also a member of the Technical Program Committee for the 7th E&E Congress, which is virtual. And this committee was responsible to plan and manage the technical program of the Congress. So today I will be the chair of this session, timekeeper as well, and I will manage the live Q&A parts. You have a chat window where you can ask your questions. And in order to facilitate my task, I would be grateful if you can start your question with the name of the speaker to whom your question is addressed. Each attendee has the capability to upvote the questions asked by others. So I will then select the question and ask the question to the chosen speaker who will respond live to your questions. So please do not be shy. And I'm looking forward to receiving your questions by chat. So now please focus your attention for the next 30 minutes on the respective presentation of our first 3 selected speakers who will present their work. So now let me introduce our first speaker. Our first speaker today is Dr. Martin Hugener from EAPA. Martin Hugener is a senior researcher at EAPA, the Swiss Federal Laboratories for Material Science and Technology in Switzerland, leading the asphalt group of the Concrete and Asphalt Laboratory, together with Professor Pietro Lura. Currently, his main research topic is asphalt recycling with special emphasis on rejuvenating agents and aging. He is an active member of the RILEM Committee on Reclaimed Asphalt and chair of task group on asphalt binders and additives for reclaimed asphalt, together with Augusto Canone Falchetto from the Aalto University in Finland. He will present today some results as part of the work performed in the RILEM Task Group 3, which carried out a worldwide inter-laboratory testing campaign on the aging behavior of binder blends containing asphalt recycling agents.
Welcome to my presentation on the aging of rejuvenated wrap binder, a RILEM interlaboratory study. My name is Martin Hugener from EMPA, but as you can see, this is the work of a lot of people from all over the world in the community of RILEM, in the technical committee of RAP. In the RILEM Task Group 3, led by Augusto Canone Falchetto from Aalto University in Finland and myself, we were interested in the aging behavior of binder blends containing asphalt recycling agents. As you know, recycling of asphalt pavements is increasing worldwide with a goal of circular economy in mind. So this means that more higher and higher contents of reclaimed asphalt are used, and at a certain point, a normal bitumen is not able to soften or recover the original properties of the binder. In that cases, especially if very high RA contents, you need so-called ARA, an asphalt recycling agent, sometimes also referred as a rejuvenator. However, these ARAs often come from another source than crude oil and hence have a very different chemical composition. And we think we know the aging of bitumen quite well, but how will it be if we add some unknown chemical? Would be the aging of this blend the same? So this is actually the question which we try to answer in this RILEM TG3 interlaboratory testing campaign, where 17 international laboratories did take part. So what did we do? First, we had to decide that we stay on the binder level, because when you go to the asphalt mix level, you have additional impact factors. So for the start, we decided we wanted to make the impacts as little as possible. So what you need is actually a reclaimed asphalt binder, a virgin binder, and a small amount of ARA to produce an N-inch binder blend, which has more or less the same properties as a virgin binder you use in this case. Then you test it. You make the short-term aging using a rolling thin film oven test. Then you test again and make the long-term aging using the pressure aging vessel. Then you test again this blend. Actually, this looks quite straightforward, but still we had a little problems to solve. For example, the reclaimed asphalt binder, you cannot buy it from a company. You have to make it by yourself. This means that you have to extract the reclaimed asphalt and recover the binder. So we had to choose between sending out the reclaimed asphalt to every lab, and then every lab can do the extraction, the recovery by themselves. But knowing that there are quite different procedures and different solvents used for these steps, we were looking for a laboratory doing this whole procedure alone. And we were quite lucky to find that the University of Braunschweig had enough capacity and extraction machines to do that. So they delivered us actually 5.5 kilogram of reclaimed asphalt binder. But still, if you divide it by 17, you only get about 300 grams of this binder, which you have to test and age. So you test it out in the 3 stages. So we don't have a lot of material for testing. So we need some test methods which don't use a lot of material. And these are mainly softening, puncturing, and ball, and DSR measurements. However, penetration is still a value which is well known, especially among practicants. And that's why we also included for a few labs the penetration tests. And we also needed a way to look at the low temperature properties, which we were doing with a bending beam rheometer equipment. But this is also using a lot of material, even though it's only once made at the end of the long and short-term aging. So a few labs did also perform this BBR testing. As an alternative, actually, we have the DSR 4mm plate geometry measurements, which also gives us information on the low temperature properties, but it's not really ready yet to do it, and not a lot of labs has these possibilities. Also, the FTIR, infrared spectroscopy, is a method which doesn't need a lot of material. And some of the labs did also perform this. So what we actually want to do is to simulate the recycling or the production of hot mix asphalt with 60, 80, and 100% of reclaimed asphalt. So you would need 60, for example, for a 60% rate, you would need 60% of reclaimed asphalt plus 40% of virgin material, which is binder and aggregate. If we break it down to the binder level, this is 60% of reclaimed asphalt binder plus 40% of virgin binder, plus a small amount of ARA just to soften the reclaimed asphalt binder to the same target value as a virgin binder in this case. So by that, the ratio of the ARA and the reclaimed asphalt binder is constant, so it doesn't matter how much a virgin binder we are adding. The target value is quite important, which we choose, because not every method gives the same ARA dosage, but we did choose the penetration value because it's commonly used, but other methods are also possible, like softening point ring and ball, ESO, G star, that's also an option. So the first step was then pre-study to determine the optimum dosage. So if we start with the reclaimed asphalt binder, we did add 5 and 10% of ARA, and you can see that with 10% we are a little bit above the virgin binder properties, a little bit softer. So we decided to use 9% for this interlaboratory study. So then, to assess the results of these binder blends, we have to compare it to something because we don't have any requirements to meet. So we used the virgin binder we also had as additional binder, which we did age in the same way, short-term aging and long-term aging. And you see we come from the penetration of about 60 down to 25 penetration value. It's still quite far away from the reclaimed asphalt binder penetration, which is about 15. But this was actually not the goal to reach that. What we also can see here is that the reclaimed asphalt binder, although it's even quite hard, it's still aging, not in the same amount as the virgin binder, but especially if you look at the softening point, ring and ball, it is aging about 10 degrees. So having that, all the labs were able to do their binder blends, aging them, testing them, and what I do present here are only the results from the softening point, ring and ball, and penetration, because we don't have time for more. So you see here, as an example, the 60% binder blend, and actually it's quite the same result as with the 80% 100 binder blends, so I don't have to show them all. You'll see clearly the virgin binder, how it's aging like before, and the results of the 4 labs which did perform this testing and aging. And it's surprisingly that the results are quite consistent. They are in parallel to the aging, so the aging is really, really the same as the virgin binder. If we look at the results of the softening point, ring and ball, where we have more results, we have, I think we have 16 or 17 results. So we also see the scattering better. So actually the precision is quite nice. And what you see is that the aging is really you cannot distinguish the aging from the 60 or 80% blend from the virgin binder. The pattern is almost exactly the same in the unaged, short-term, and long-term aged stage. So for the low temperature properties, we only have 4 results from 4 labs, but it's covering the whole ratio, 60 to 100%. What you can see that from the reclaimed asphalt binder, when we make the blend and age it, at the end, we have similar results for the blends like the virgin binder here on the left. Even a little bit better if you look, for example, at this, the critical temperature of the stiffness. We have for the virgin binder around 15, and for the blends, they are all about 20. So it's really nice results which we did obtain for the low temperature properties. So the conclusion overall, the effect of the ARA was not lost after aging, and this did not exceed the aging of the virgin binder, independent of the ARA content and also independent on the temperature range, low temperature, intermediate temperature, or high temperature. So actually the protocol we used in this interlaboratory study showed quite high reproducibility, unless when we didn't have enough results. So that's why we are actually now working on a RILEM recommendation for the evaluation of ARA blends in hot mix asphalt. So these are not all results we have produced. You will find them in the story report, which is not yet published, and some other publications which will come or have already been published. So thank you very much, and wish you a nice time.
Thank you, Martin, for your overview of this interlaboratory study managed by the RILEM and these interesting results on the aging of Rejuvenator wrap binder. I'm now very pleased to introduce our next speaker, Aibo Ding from Queen's University. Aibo Ding received his PhD degree in road and railway engineering from Southwest Jiaotong University in China in December 2018. Between 2016 and 2017, he studied at Queen's University in Canada as a visiting PhD student under the supervision of Professor Simon Esp. And after his PhD, Aibo spent 1 year again in Esp's lab as a postdoctoral researcher. In June 2020, he joined the School of Civil Engineering, Southwest Jiaotong University, as an assistant professor. Currently, Aibo's research mainly focuses on the durability of asphalt pavement materials. Aibo will present some results from his work at Queen's University on aging and field performance of polymer-modified bitumen.
My name is Aibo Ding. I would like to thank the organizers of the European Congress for working hard in order to make this meeting happen as a virtual event. I would also like to express thanks for the financial and in-kind support of this research. Ontario has constructed many pavement trials over the years. This slide shows only the more recent ones investigated over the last 13 years at Queen's University. Today, I will discuss results from Timmins, Ontario, which is about a 10-hour drive by car north from Toronto. This trial was built in 2003, and the section of highway will soon need to be reconstructed as it is reaching the end of life. Samples tested were original materials as well as binders recovered from core samples taken after 5, 8, and 15 years of service. The purpose of the trial was to validate and, more importantly, find ways to improve upon the superpave cracking specifications. So, all sections were constructed with binders of nearly the same continuous low temperature grade, ranging from -35 to -37. A variety of modification types were used to obtain the grades, and even as early as 5 years, this showed up as significant performance differences for ostensibly the same superpave grades of PG-34. Here are two representative photographs of the best and worst performing sections after 16 years of service. It is obviously that Lloydminster asphalt modified with a small amount of RET polymer performs very well, and that West aging oil residue tainted binder from Ontario has not done too well. This is not a good result for the superpave specification, as both binders were supposed to provide similar performance, whereas in fact they perform on opposite sides of the spectrum. The recovered high temperature grades for grades show that some of these sections have hardened significantly. Changes from the original contract high temperature grades range from a low of 8 degrees for the stable Lloydminster binder to a very significant 35 degrees for the Ontario binder that was tainted with about 10% waste aging oil residue. We have recently spent a lot of effort on evaluating beta low temperature properties and come to the conclusion that the limiting 13-degree phase angle temperature is a much improved property over both the regular BBR and extended conditioning BBR temperature grades. It can be measured in a matter of hours and provides improved precision and a similar accuracy to the extended BBR grades. For this set of binders, though we can see that the PAV residues are again falling in a rather narrow range, while the recovered binders are more in agreement with field performance. However, sections 1 and 7 grade similarly, which is not in agreement with their field performance, so there is more to the story. So to capture not only the limit, but also the rheological type of the binder, we have introduced the delta TCD, where C stands for the limiting critical phase angle and the complex modulus G star temperatures, and D stands for DSR. We can see once again that there is a reasonable spread for the PAV residue, but the recovered binders are significantly more spread out. So this once again points to the inadequacy of the RTFO and PAV aging protocol. We have tested the samples for their gel point, which is rheological defined by the Chambon-Winter criterion, which states that the tension delta is independent of the frequency at the gel point. For the 6554 binder, the gel point is quite clear in the PAV residue, but disappeared after only a few years of service. For binder 6555, which has a high vinyl content, the backbone of the polymer remains intact and the gel point is still visible after many years of service. However, because the base binder was not of good enough quality, this section also cracked quite severely in early age. FTIR analysis of the lab-aged and the recovered binders confirmed once more that the PAV residue is not aged sufficiently. It would likely be better to age for 14 hours or even longer and in thinner films, as we have published at a past Eurobitume Congress in Istanbul. Aging for 14 hours brings the level close to what is obtained for 8 years of service. The findings for the SBS integrity were not encouraging, as we were able to recover most of the styrene, but the butadiene functionality saw a precipitous decline, and after only 5 years of service, the butadiene group index was reduced by anywhere from 25 to more than 75%. This shows that after 8 to 10 years of service, the effect of the polymer is almost gone when it is most needed. In summary, the PAV protocol that uses RTFO, PAV, DSR, and BBR methods is woefully inadequate and thus must be improved. The limiting phase angle temperature needs more attention, as it provides grades that are much better than those obtained by the regular BBR. are much more precise than those obtained by the extended BBR that use 72 hours of conditioning and are as accurate or more accurate than extended BBR grades. The delta TCD provides a handle on the shape of the rheological master curve or the soil versus geotype, and as such is a good complement to the limiting phase angle temperature. Finally, SBS polymers have proven rather disappointing in terms of their ability to provide much toughness when it is most needed in old age. Numerous test sections in Ontario have failed to provide much benefit for the control of cracking when polymer is added to poor quality base binders. So the jury is still out on whether there is a cost benefit for the use of such polymer modifiers. This is where I wish to end the presentation, and I or Professor Hisp would be happy to answer any questions. Thank you.
Thank you, Aibo, for your presentation addressing, again, aging of binder, but looking at different perspective with the, looking at different modifiers and how these modifiers perform on the field. So now let me introduce our third speaker, Frederick Delphos from Eurovia. Frederick Delphos is a physico-chemical engineer. He joined Eurovia company in 1998 as a research engineer on emulsion and cold mixes before becoming project manager on different research programs on asphalt. He is currently the director of the research center of Eurovia, based in France, close to Bordeaux. In the research center, there are 33 people working on numerous international research projects, such as asphalt, coal products, innovative additives for road industry, development of new mechanical tests for hot mix asphalt, road marking, aggregates, railway. Today, Frederick will present some work allowing to establish correlations between bitumen and asphalt mix and highlight the importance of long-term aging tests to better assess mix performance.
Good afternoon, everyone. My name is Frederick Delphos. I'm a technical director of the research center. My presentation deals with the relationship and correlations between bitumen and asphalt mixtures. Before starting, I would like to thank my colleague from the research center and from the technical direction of Eurovia. In the last years, we observed a significant evolution on the European market. French and European refining is currently in a phase of rationalization and search for maximum flexibility in crude supplies. European refining are ongoing rationalization on changes, evolution in crude oil and refining processes, but also with an additive market expansion, emerging with a lot of bioadditive, etc., but also for economical reasons, trading supply imports. These different points create concern about the quality and consistency of products delivered, especially as the European standards appears to them as insufficient to ensure satisfactory performances of the finished products, particularly in case of specific products such as high modulus asphalt, polymer modified bitumen, and bitumen emulsion. Contractors are worried about bitumen quality, and we observed on field some negative feedbacks. They always ask us the same question: how to evaluate the quality of a given bitumen in relation to its intended use, of course, with simple tests and now. So in this context, we launched a research program some years ago to the search for new relevant indicators on bitumen to predict product properties. This presentation will focus on asphalt mixtures. In this study, we selected 14 bitumen of 3 different grades and origin. These grades correspond to PG 64-22 up to 66-10. These bitumen are named B1 to B16. These bitumen were analyzed by numerous tests, all conventional European tests like needle penetration, ring and ball, etc., but also by some rheological tests by DSR. Isotherm at different temperature, the MSCRT CR test, but also by the bending beam rheometer, and we define the TS value, the temperature at which the stiffness modulus equal 300 MPa, the TM value, temperature at which the slope of M of the log S measure log time versus log time curve become equal to 0.3, and from these two values we calculate delta TC. So we manufacture 14 hot mix asphalts with diorite aggregates. For all these mixtures, the binder content is the same, 4.9%. For this mixture, we fix the VMA and VFA. On this mixture, we perform the following tests: the weld cracking test, the stiffness modulus according to different methods, the fatigue test, and the TSRS test, which is the thermal stress restraint specimen test. After and before aging, according to the RELAM procedure, 4 hours at 135 degrees C and 9 days at 85 degrees C on the loose mix. On the graph, on the left, we can see correlation between routing test and ring and ball temperature. The superposed parameter critical temperature, which is the temperature at which G star on C delta is equal to 1 kPa. The temperature for which G star on C delta appear higher than a real ring and ball temperature, more than 10 degrees C. The results do not show direct correlation between bitumen characteristic and asphalt routing properties, but rather temperature threshold for ring and ball and the shaft temperature, below which routing is likely to occur. On the right, the graph shows the correlation between the percent routing of the asphalt measured after 300 cycles, 1300 cycles, as a function of the GNR value. It shows a flat trend with, again, a threshold-like behavior around a GNR value of 1 Pascal at 3.2 kPa stress level. For neat bitumen, we observe the same tendency from these different tests. Those thresholds will be strongly dependent to be aggregate composition. For stiffness modulus, we know the bitumen stiffness G star value is generally considered as a good indicator to predict the asphalt stiffness modulus. This is confirmed by these results on the right. For both stiffness modulus method, we observe a very good correlation with the G star value, with the R square close to 0.9. Since Eurovia has developed a specific rheological model, which from different types of aggregates, allow to predict compression stiffness modulus by NAT, but also by other method, to predict from the G star, VMA, and VFA the stiffness modulus of the hot mix asphalt. To predict fatigue performance from bitumen property, there is no reliable criteria at the moment. On this presentation, we present a new indicator, which is the susceptibility to loading time of the phase angle. The calculation of the slope of the phase angle versus frequency at 10 degrees C presents a satisfying correlation with fatigue behavior of asphalt at 10 degrees C. The higher the slope of the phase angle isotherm, the lower the asphalt fatigue resistance is. For the low temperature behavior, on this slide, we try to correlate the TSR value to the TS and TM and thrust temperature from the for the unaged bitumen. We don't notice significant correlations between TS and TM value. We didn't measure significant correlation. This graph presents for TS and TM and thrust temperatures the impact of aging after 1 PAV. Relevant differences are measured. Gap between unaged and aged bitumen highlights the importance of simulating aging when analyzing low temperature properties. Some bitumen are more sensitive to oxidation than others, and their low temperature performance can be strongly impacted. First temperature increase from 5 to 9 degrees C after PAV, and for TM, we observe a delta up to 10 degrees C. This graph presents evolution of the delta TC, which is the difference between the TS and TM value after PAV. This parameter appears as an interesting indicator to illustrate this asphalt oxidation sensitivity. The higher the increase in delta TC value, the higher the sensitivity to oxidation and the lesser the pavement durability. This criterion has shown a high potential to capture binder embottlements and pavement premature cracking in the North America, where it is now extensively studied and discussed. To confirm the importance of testing low-term and age asphalt mixes, we measure TSRT value for 3 different bitumen on which we apply the rhythm aging procedure. On the first graph in green, we can see relevant differences on asphalt mixture between these 3 bitumen. Bitumen B6 show a very dramatic decrease in its TRST value. Before aging, we have -25. After aging, we measure -6.8 degrees. For the other bitumen, B2 and B4, the difference is very is -10 degrees C or 7 degrees C against 18 degrees C. These results are well in line with the previous results on binders. On the right, we can see correlation with the TM value after aging, and we observe a very good correlation only on 3 points. To conclude, this study allows to present relevant bitumen indicators to predict hot mix asphalt properties. G star for stiffness modulus on asphalt, the slope of the phase angle at 10 degrees C from the isotherm with fatigue test on asphalt. For the routing threshold effect with ring and ball temperature at which G star on 6 zeta equal 1 kPa appear as interesting, but this test is very sensitive to aggregate shape. For low temperature behavior, poor correlation between unaged asphalt mixes and bitumen. BBR critical temperature or thrust values appear as quite interesting for neat bitumen, but most after aging. The delta TC parameter seems to be very interesting as a TM value to predict the sensitivity of aging at low temperature. This relation between bitumen and asphalt mix performances must be expected to be also largely dependent on mix composition parameters. Additional tests are in progress to evaluate the impact of VMA and VFA values. Thank you for your attention.
Thank you, Frederick, for your presentation and showing us the correlations which have been established between bitumen and the asphalt mix, and showing us the importance of the long-term aging to assess the performance of the mix and looking at fatigue and cracking properties. I will now ask our 3 first speakers to open their camera, and I will go through. So please, Martin, Aibo, and Frederick, if you can open your camera, and I will go through the Q&A. So the first question would be for Martin, and dealing with rejuvenator. What do you consider as a rejuvenator, or a good rejuvenator, I should say? And do you take into account these viscosity grades such as the V1200 or V1500, or only other products? So what is for you the definition of a good rejuvenator to be included in RAP?
Thank you for the question. I think this is a very difficult one because this is not really to answer. What you have to look is what the rejuvenator is doing. You cannot say from the composition alone whether it's a rejuvenator or not. So you have really to make the test. So what we have done, and see whether a rejuvenator can restore the original properties. with very soft bitumen, you also have to be very careful because they often already contain some kind of rejuvenators because some companies already mix in some oils or anything.
And if I'm looking as well on another question dealing with rejuvenator, the question was what factors or characteristics should be considered in a rejuvenator? And which is linked to this this first question. What are you looking at? What are the properties you are looking at? And I will add in your study, so you have addressed only one rejuvenator. Are you planning to address other rejuvenator and to assess their performance?
Actually, we had in mind to do that, but because of the quite a lot of work, only a few laboratories were able to do some additional studies. But for the most of the results, we only have it for this one bio-based rejuvenator. Actually, we don't look at the properties of the rejuvenator itself. We just look what he can do with the binder. And so actually, we are looking at the binder blend. And this is why we are developing a procedure, a protocol, how to assess the quality, if you want, of a rejuvenator. But this is always combined with the reclaimed asphalt binder and also with a virgin binder you add. So I think this is a better process to evaluate whether a rejuvenator is good or not so good. I think, yeah.
Thank you, Martin. Maybe I will ask the next question to Aibo. So there is one question for you, Aibo. It is interesting to see that the lab aging is not good enough to simulate the field aging of SBS modified bitumen, so using RTFOT and PAV. And do you have any suggestion for furthering the good lab simulate for PMBs?
Yeah, I think it's better to use like thinner film thickness and a longer conditioning time in the PAV, so we can simulate the field aging of like SBS modified asphalt binder. Yeah.
Thank you, Aibo. One question for you, Frederick, maybe. Did you include PMB in your study? You have presented a lot of results on neat asphalt. So did you are you looking at PMBs? And do you think the parameters presented are relevant for PMBs?
As I mentioned during my presentation, we have a global research program. This presentation is focused on neat bitumen, but of course we have a global research program as well as for PMB, but also with RAP. So with different additives, with different polarity, etc. So we are going to publish in the next month, next year, all the results, and we will see the impact of to select a relevant test in order to correlate PMB or binder with additive with hot mix asphalt property. Sometimes when we have a high polarity of some additives, we can see we have some difficulties to correlate with hot mix asphalt property after, for example, if you soak your sample in water, we could have some chemical reaction that we don't take into account at the moment because a bitumen is an hydrophobic product. As soon as we modify, as well as we modify this property, we could have some chemical interaction with aggregates. So we are going to publish all these different results in the next months.
Thank you, Frederick. Due to the time constraints, I will not have time to go through all the questions. However, and I will come back to that later during the session. Some of you, some of the attendees might have noticed that there is a specific chat open on the networking lounge with for each session, there is a chat available. So you can go into that chat and ask and continue the discussion with our speakers. So for that reason, I will stop the first Q&A part because it's already 3:15, and I will ask our three speakers to close their camera. Thank you. And I will now start the second part of this 2B session. And our next speaker is Franz Bohmert from the Federal Highway Research Institute. After studying civil engineering, Franz Bohmert began his career at the Federal Highway Research Institute, better known as BAST. For more than 20 years, he has been assigned to the section Asphalt Pavements, where he worked as a technical officer. Franz is a member of several national working groups for technical regulations and also the European Committees for Standardization. A current focus of his work is the quality assurance of the test laboratories that are allowed to test road construction work for the public road authorities. His speech today presents the Tensile retardation test, a modern variant of a creep test, which has been used for different binders and asphalt mortar. The effects of binder modification and the stiffening effect of fillers are presented.
Dear Congress member, wherever you follow this presentation, I warmly greet you. When the news reached me that I'm invited to present our paper at the Congress, I was very pleased and at the same time a little astonished. The creep test, albeit with a special feature, made it into a technical session of the E&E Congress. 10 minutes is not a lot of time, but it should be enough to arouse your interest in the full paper. In addition, the slides are suitable to present some things more clearly than in the paper of the proceedings. That's the principle of the tensile retidation test in 3 sketches. A constant stress is spontaneously applied at a constant temperature. Thereupon a deformation, a change in length, occurs in the test specimen, which after a certain time runs straight line with the time. According to the European standard, this test principle is used on asphalt. There it is referred to as the tensile creep test. We have adapted this principle for binders and mortars. Here you can see the schematic structure of the test facility. All 3 elements of the test equipment, the step motor transmission, the measurement of elongation, and also the force measurement are connected to each other via a computer with real-time control and work with high resolution and precision. Compared to the precise and high-resolution measurement technology, the test specimen appears coarse in terms of its dimensions. In the middle part, the specimen has a cross-section of 1,000 square millimeters. For the binder and mortar test, this cross-section can be assumed to be true for the sample examined. In this video clip, you can see the tensile retidation test in time-lapse. The top of the specimen is marked. It can be seen that the main part of the deformation and at the same time a cross-sectional tapering takes place in the middle part of the test specimen. And here's a special feature of this test method. The tensile force is adapted to the tapering cross-section in such a way that a constant stress prevails over the entire duration of the test. An individual test is evaluated by considering the linear course of the deformation at the end of the test period. The slope of the deformation curve is set in relation to the constant stress applied. From this, lambda z, the tensile viscosity is calculated in units of megapascal seconds. The evaluation for the tensile retidation test is as follows. The diagram area is spanned by 2 axes. The viscosity is plotted vertically in units of megapascal seconds. The scaling of the vertical axis is logarithmic. The test temperature is plotted horizontally. The temperature scaling is linear. Usual and proven test temperatures for binder and mortar are from +5 to -25 degrees Celsius. Each point gives a result for the viscosity lambda z. A regression line with a general function y is equal to m times x plus b can be determined from the single tested tensile viscosities determined at the various temperatures. The coefficient of determination of this regression is usually better than 0.98. After the explanations of the test principle, the evaluation and the presentation now results that we achieved with the tensile retidation test. Here you can see the viscosity characteristics of 5 paving grade bitumen from one manufacturer. The coefficients of determination of the regression lines are all close to 1. The results are convincing for the various penetration classes of the binders. These are the same 5 regression lines for the 5 paving grade bitumen. The scaling of the axis has been changed. The vertical axis was extended into the range of low viscosities. The horizontal axis has been extended into the area of higher temperatures. The softening points of the bitumen correspond very well with the viscosity characteristics. The test method tensile retidation test is also suitable for illustrating the effects and changes of binder modifications with wax or rubber or rejuvenators. To keep the time frame, I refer to the full paper in the proceedings. The tensile retidation test can also be used for asphalt mortar. The stiffening effect of the filler in the asphalt mortar requires greater forces when carrying out the test procedure, so that sufficient and measurable deformations also occur. We received binders from these 2 research projects for our investigations on mortar. These are polymer-modified binder of same types, but from different manufacturers. In the 2 research projects, different asphalts were tested, both on the warm side with regard to the resistance against permanent deformation, and on the cold side with regard to resistance against low temperature cracking. For our investigations with the tensile retidation test, we simulated the mortar receipts of the various asphalts. For this purpose, we had the identical binders from the 2 research projects. Comparable aggregates, that's limestone filler and crushed diabase sand, possibly from another source, were used for the fillers. 3 of these mortars were made with a binder of same type, but from different manufacturers. 1 mortar was made with a softer binder, that's the green line. The filler binder ratio, as well as the ratio of added and own filler, is identical for all 4 mortars. The regression lines and the viscosity characteristics differ obviously. The orange and the blue lines intersect at about 6 degrees Celsius. They have different inclinations. The purple line and the green line run almost parallel, but are shifted by 0.8 powers of 10. In 2 research projects on the qualities of the polymer-modified binders, asphalts with these binders were investigated. Here we link the viscosity characteristics of the asphalt mortar with the failure temperatures of the TSRST, of the corresponding asphalts of the research project. It turns out that the failure temperatures cover a range of approximately 6 Kelvin. Projected onto the viscosity characteristics, the values of the mortar viscosities at all failure temperatures are around 10 to the power of 7.5 megapascal seconds. Now we derive a statement about the resistance against permanent deformation from the viscosity characteristics of the mortar. We change or extend the axis for the viscosity and temperature in warm surface temperature range. And also we extend the regression lines for the viscosity characteristics into the warm surface temperature range. The test method for assessing the resistance against permanent deformation is the cyclic compression test, which is carried out at a test temperature of 50 degrees Celsius. When considering the criteria number of load cycles, epsilon for the strain and epsilon star for the strain in the turning point of deformation, the same assessment of the resistance against permanent deformation is carried out, as also shown with the ranking of the mortar viscosities at 50 degrees Celsius. So here too, there's a congruence between the results of the 2 test methods. To keep the time, a short summary. The tensile retidation test is a robust and at the same time sensitive test method. You can use it on binder and mortar. The characteristics of viscosity describes the temperature sensitivity of the binder and mortar. The test method illustrates the effectiveness of modifications. The test method offers the presentation and assessment over the entire surface temperature range. It's a single test method for the competing properties of asphalt on the cold and the warm side. The test method can be used very well for the mix design. First, the selection of suitable binders, and further for suitable composition of the mortar. Thanks for your attention in the virtual audience, and a special thank you to the co-author, Ms. Franka Wünscher.
Thank you, Franz, for your presentation addressing this test, this tensile creep test on binder and asphalt mortar. So I will now introduce Jeremy Adams from the Western Research Institute. Jeremy is a chemist specialized in organometallic catalysis, photochemistry, and supramolecular chemistry. He began his career at the Western Research Institute in the area of petroleum characterization and processing, working on multiple items such as the asphalting chemistry, fouling, emulsions, waxes, and coking. He helped as well to initiate the Asphalt Industry Research Consortium. Recently, he has been working on bringing value to undervalued hydrocarbon sources, including developing asphalt and asphalt additives from Wyoming coal, while also working on a variety of other hydrocarbon characterization. He is also the principal investigator on a Department of Energy project to produce carbon fiber from lightweight vehicles. He will present today some findings dealing with bitumen composition analysis.
Welcome. My name is Jeremy Adams. I'm the program manager of hydrocarbons at the Western Research Institute. Up on the video, we also have Jean-Pascal Planche with us. So I'm going to be speaking about innovations and developments in bitumen compositional analysis. So here's the outline of the presentation. So why do we care about characterization of bitumen? Well, it's a highly complex material, literally containing hundreds of thousands of different molecules, from things that are very hydrogen-rich, saturated alkanes, to things that are very polar and aromatic with a variety of functional groups, and a whole set of molecules in between. And it's this balance between these different molecules which helps hold this material together and makes a stable material. And so one of the reasons that we're very interested in this is that binder variability has become a very big issue in the last 15 or 20 years because of a lot of changes in crude oil sources, but also in refining practices. Refiner is no longer just doing a simple distillation. They have a variety of things trying to extract value out of the petroleum, and at the end they'll take and formulate a new product, the bitumen. And so a lot of characterization methods out there are not able to capture all of these changes. They're too narrow, and we need a new, more holistic approach at looking at the composition of bitumen. So at WRI, we have a long history in characterizing bitumen and also asphaltenes. This started well before the Sharp days and has continued to today with a variety of industry projects, and particularly through our Asphalt Industry Research Consortium, AIRC. So in this program, we have characterized over 100 different asphalt bitumen samples, and we have a whole wide range of materials. They have a variety of different processing conditions that were applied to these materials, such as vis braking and air blowing, but also a wide range of modifications that have been done through polymers and different additives. So one of the tools that we've used to help us to understand, differentiate, and predict properties from these materials has been our SARA AD separation. So this separation is a combination of chromatography for the saturates, aromatics, and resins, and solubility for the asphaltenes. So here's a typical chromatogram shown here that we get from our separation. We can see we have one saturates fraction, we have 3 aromatics fractions, we have a resins fraction, and then we have 3 fractions of asphaltenes. So this is something very unique and patented by WRI. And this can tell us a lot about the performance of bitumen materials. So one of the things that we have wanted to do was to understand more of what kind of molecules report to these fractions and how does that help to build the structure of the bitumen. one thing I want to point out real quick, there's a plot highlighted in red here. This is just showing that the amount of asphaltenes we get from the Serra AD separation, the total asphaltenes, is very consistent with the amount of asphaltenes you would get from doing a benchtop precipitation of asphaltenes. So if we look at these different fractions, the saturates fraction can have linear saturated alkanes, but it can also have highly cyclic materials as well. That's shown here. The aromatics 1 fraction is very similar. It has a lot of aliphatic character, but there is one aromatic ring on most of these molecules, but it doesn't change its properties significantly from saturates. The aromatics 2 and 3 fractions contain aromatic rings that are fused or joined together by carbon-carbon bonds. Aromatic 2 fraction are 2 and 3 ring aromatics. It can have some 4 ring pyrene type structures. The aromatics 3 fraction contains the larger aromatics, and this fraction is very important in the properties, stiffness properties of the maltenes and also interactions with different polymers. The resins fraction can have a variety of structures, but the main thing here is that it has the presence of some heteroatoms in different types of functional groups. So these can be oxygen, nitrogen, or sulfur. The asphaltenes, this is still a complex set of molecules, and we don't have good model compounds, but we're understanding more about them, especially the nuances between island and archipelago. The main thing that we've done is to really help the world see that there are different types of asphaltenes. You know, there was a development of understanding in the past from Bo-Sen-Go, who said, you know, there's one class of molecules or one molecule that can be isolated as an asphaltene. Richardson later said, no, it's a whole complex set of molecules. And at WRI, we said, no, it's actually, we can go further. There's actually different classes of compounds that can be extracted in the asphaltenes. And we've done this by using solvents of different solvent strength. So this is the solubility portion of the separation. So we'll separate asphaltenes by using cyclohexane, toluene, and dichloromethane. And so these are solvents of increasing solvent strength. So the figure at the left is basically showing a Serra AD profile of different types of hydrocarbon materials, from coal, shale, asphalt type materials like gilsonite, and different petroleum materials processed in different ways. The figure at the right-hand side is showing a radar plot of the compositional space of different paving grade bitumen. So this has allowed us to do a lot of work in predicting properties and differentiating materials. One of the things that is also very important that we can get from this method that you can't from others is that we can tell if your material has been cracked. And this is important because of IMO 2020. And a lot of marine fuel oils have in them is a big outlet for cracked bottoms from different processing methods. And these cracked bottoms are not desirable in asphalt for paving because you've lost a lot of the aliphatic side chains, and so it cannot relax stresses. And a lot of times, if you can't relax the stresses, it can lead to cracking, especially at low temperatures. So these are 2 different bitumen that were pyrolyzed at different times, and we're only looking at the cyclohexane asphaltenes and the dichloromethane asphaltenes. We can compare the ratio of the 2 and get a coking index, and this can show us very clearly if our material has been cracked. And so here are some examples. We can take bitumen 1, we can vis break it, and we see the coking index goes down significantly. If it's processed under more severe conditions, like in a hydrocracker, again, you can see there's this significant decrease in the coking index. Fluidized catalytic cracker bottoms don't have any cyclohexane asphaltenes because they've been heavily processed. Another example, here's bitumen 2. If we blend that with hydrocracked bottoms, again, you can see there's a dramatic change in the coking index. And again, here are 3 different bitumen at the end, which show different severities of vis breaking. So this coking index is a great metric for us to diagnose and understand and see, do we have cracked materials showing up in the bitumen pools? So this method, again, is useful for a lot of things, but it can track oxidation very well. So here is one asphalt that has been oxidized to different levels of severity. We track this through a carbonyl and sulfoxide from the FTIR and by the Serra AD. If we focus on the net change, we see that aromatics 2 and 3 decrease, toluene asphaltenes increase, and that dichloromethane asphaltenes increase. This has implications on the performance and the behavior of the material. We know oftentimes that as asphalt oxidizes or bitumen oxidizes, it becomes more brittle. So we can also compare the changes in oxidation to a colloidal instability index, which is calculated from the Serre AD fractions. And we can see that it tracks very well. And also for the performance of the material through delta TC, which is kind of a cracking parameter based on the relaxation of the material. This is directly related to the composition and changes in the composition. So with this method, we know it doesn't tell us everything. We do occasionally run into a situation where we'll have two materials with a similar profile that behave differently with an additive, or two materials with the same properties, but they have a slightly different profile. So there's some chemical reasons that underlie this. So we're developing second generation method, which looks at size exclusion chromatography to tell us something about the size of the molecules in the fractions. Upper right hand is showing us that we can look at the aromatic structures within those fractions using fluorescence spectroscopy. And then we're also developing an FTIR method so we can track the changes in the functional groups of these materials. So to wrap up here, we have a new method that takes advantage of chromatography and solubility together in the same system. And we can separate materials, which is very helpful for fingerprinting. We can even map crude oil sources of different bitumen. We can predict physical properties. We can diagnose fizz breaking and other upgrading methods and air blowing. We can track oxidation. We can track polymer compatibility of the different materials. And we can look for additives. We have a lot more insight now because of our model compound study, but we do recognize that we have some limitations. And so we're addressing these limitations by adding additional ways to look at the fractions and drill down further and see why these are different. And this is showing a lot of promise. So that our end goal is really to help suppliers and users to design bitumen, to buy and purchase and use the best bitumen for their application, and to help them understand that there's a whole variety of changes that are occurring at the refinery level, and to diagnose these and to get around them. So we would like to thank some of our supporters, so the University of Wyoming and School of Energy Resources for the model compound work, and then our Asphalt Industry Research Consortium members. Thank you.
Many thanks, Jeremy, for going through the use of the Sarah AD tool to address the composition of binders and how the composition of binders can explain the behavior of some binders. So our last speaker for this session is Thalita Nascimento from the University of Sao Paulo in Brazil. Thalita Nascimento is a civil engineer and has a master's degree in transportation engineering. She is currently a PhD candidate in transportation engineering at the University of Sao Paulo under the advisory of Professor Adalberto Faxina. She was a guest researcher at the Ruhr-Universität Bochum in 2020, working with infrared analysis. Her research area includes studying the effects of photooxidative aging on bitumen and asphalt mixture properties. The work presented today addresses the effects of ultraviolet radiation on the fatigue life of modified bitumen and is part of her and Daniela Garcia's master's thesis.
Good afternoon, my name is Thalita, and I would like to thank you for the opportunity to present the work we are developing at the Department of Transportation Engineering of the University of São Paulo in São Carlos, Brazil. I will present the work Evaluation of the Fatigue Life of Modified Bitumens Aged on the Ultraviolet Radiation, which I developed with Daniela Garcia and our advisor, Professor Adalberto Faxina. The oxidative aging extends over the pavement lifespan and is one of the main reasons for bitumen hardening. The formation of chemical functional groups containing oxygen, such as sulfoxides and carbonyls, increases the bitumen consistency. The excessive hardening can be negative since it contributes to premature fatigue cracking in pavement subject to high deflection. Some test protocols are available to simulate the field bitumen aging. In general, these tests simulate only the effects of temperature and oxidation. However, the effects of ultraviolet radiation are not considered. Therefore, the study aims to analyze the impact of UV aging on the rheological properties of modified bitumen. It is important to choose bitumen less susceptible to photooxidative aging, especially in regions where intense UV radiation throughout the years is present, as in Brazil. Studies including various modified bitumens are necessary, as the influence of additives on the resistance to photooxidative aging is still not entirely known. The experimental plan was performed using a neat bitumen and 6 modified bitumens with polyphosphoric acid, PPA, crumb rubber obtained from Delphos tires, SBS copolymer, and low-density polyethylene. The samples were previously short-term aged in the rolling thin film oven, RTFO, and then subject to 2 different long-term aging procedures. The photooxidative one, employing a radirometer, and the thermooxidative one using the PAV. The linear amplitude sweep LAS test was performed in the aged residues to evaluate the effects of aging on the fatigue damage resistance. For the photooxidative aging, we used a radirometer equipped with 3 xenon lamps. The parameter sets for the test that we can see in figure 2 aim at accelerating the sample's degradation. For each sample, 30 grams of bitumen were spread on a metal tray in order to obtain a thin film. The exposure time to UV radiation was 240 hours. And here we can see how the bitumen looks after the UV. Regarding the LAS test, it was performed in a BSR according to the ASHTO-TP 100 to 114 at the temperature of 25 degrees Celsius. The test was divided in 2 steps, a frequency sweep and an amplitude sweep, and the results were used to adjust the fatigue model, where NF is the number of cycles to failure. The LAS results were also used to obtain the fatigue damage tolerance index, AF, related to material failure, which was proposed by Hintz in 2012. However, some materials could not be determined using the AF index, as we can see for the UV aged bitumen plus rubber plus PPA in the curve of figure 2. A possible explanation for such limitation, according to the literature, is the occurrence of adhesion problems between the sample and the metal plate, or the predominance of flow over the cohesive fracture due to fatigue. So, as an alternative to this issue, we also use in this work the approach based on the linear elastic fracture mechanics, LAFM, proposed by Nunes and others in 2016. This approach considers the macrocraft propagation in the material observed during the test. The failure criterion is the peak of the curve stress intensity factor K versus crack length A. Then, applying the LAFM approach, it was possible to obtain the crack length for materials such as the bitumen plus rubber plus PPA, as we can see in figure 3. The analysis based on the viscoelastic continued damage, VCD, shows that for a low strain level of 3%, which represents pavement with low deflections, the bitumen plus rubber and rubber plus PPA presented the longest fatigue lives for both long-term aging levels. For a high strain level of 30%, the bitumen plus rubber and rubber plus PPA also presents the best performances for both long-term aging levels. The basic bitumen presented the lowest fatigue life at 3%, but it stands out well positioned at high strains in all aging conditions. The results show that bitumen modification is generally positive at low strains, but only some modifiers can increase fatigue life under high pavement strains. When we compare the PAV and UV aging, we can note that all materials' fatigue life for both strain levels was higher on the UV radiation, except for the bitumen plus polyethylene plus PPA at 3% strain level. The results that could not be obtained from the AF parameter were obtained using the LAFM approach, which showed to be effective given that all materials had their crack length at failure determined. By comparing the results for PAV and UV aging, it's possible to observe that all samples aged in PAV presented a higher tolerance to damage when the parameter analyzed was the AF. However, when the analyses were obtained by the LAFM approach, it was the opposite. Most materials present crack length at failure higher on the UV aging condition. And for both methods analyzed, we can see that the use of modifiers increased the fatigue resistance. Based on the results, the materials were ranked from least to most sensitive for PAV and UV aging, assuming that the best ones are those with the highest fatigue lives, the highest AF, and the highest crack length at failure based on the LAFM approach. So the bitumen with the best performance is the bitumen plus rubber plus PPA, followed by bitumen plus rubber. And in the last positions, we have the bitumen plus polyethylene and the base bitumen. And to conclude, I can highlight that most materials fatigue life for both strain levels was higher on the UV radiation. For low strain levels of 3%, the effect of modifiers on the bitumen fatigue resistance is positive for all aging levels. At high pavement strains, 30%, only the bitumen plus rubber and rubber plus PPA presented fatigue lives longer than the base bitumen. And the LAFM approach showed to be an effective tool to analyze the LAS test results. Finally, I would like to thank the Brazilian research agencies, CAPES and CAPET, the University of São Paulo, the Eurosalt and Eurobitume organizing committee, and all of you for your attention. Thank you very much.
Many thanks, Talita, for this evaluation of the fatigue life of different modified bitumen using some UV radiation aging. So now I will ask our three speakers to join me, and they are there, so that's perfect. And we will have about 10 minutes to go through the questions. So give me 1 second. I have identified the point is that as we have all the questions remaining, my first question would be for, where is it? I'm sorry. Let me ask the first question to Franz. And the question is dealing with the size of the specimen that you are using to with this tensile test. And the question is, I lost it, I'm sorry. So with the rather large dimensions of the specimen, how do you avoid precipitation of the aggregate grains in the mortar during cooling?
The dimensions are really big or great for the testing we do, but it's like a natural also. We cool it down slightly for testing, but it's not at all a problem. It works always well. And it's shifted to the ends. The end plates are a little bit prepared. They are really rough, fine and rough. And that's there we got a good connection for putting in the force.
Thank you, Franz. The second question will be for you, Jeremy. Did you take into account the fact that the solubility of molecules is temperature dependent? And as an example, some researchers found that large saturates, such as C40 molecules, are not dissolving in N-heptane at room temperature, and therefore they will show as asphaltene.
Okay, very good question. Thank you. So this is true. In our system, we've used very long saturates, and we've even isolated wax fractions using MEK from highly waxy crude oils. And they do still show up in the saturates fraction during the chromatographic separation. Now, there are some very large waxes that can crystallize at higher temperatures that perhaps are showing in the asphaltenes. But we don't use this method primarily to characterize the asphaltenes, but we have a second separation, which is called the waxphaltene determinator. And this separation, again, it's based on an HPLC platform. And we use different solvents at different temperatures to get out different wax fractions. So there we can actually isolate the high crystallizable wax fractions with that. So that's a completely different platform and separation and technology that we have to separate especially the effects of asphaltenes and high molecular weight waxes. But that is a very good point. Yep.
Maybe another question for you, Jeremy, dealing with RIOB. And is RIOB showing up in different peaks in SARA AD? So for the attendees, and RIOB is refined engine oil bitumen.
Right. Yeah. So we've done a lot of looking at RIOB, and so RIOB is mostly in the saturates, but it does show up about 7 to 9% in the resins, and this resins content is the polyisobutylene succinimide additives that are added to prevent some of the carbonization, and it's kind of an anti-fouling additive that's added in the formulation. So that gets concentrated in the bottom of the RIOB during the kind of the distillation of the engine oil bottoms and the reprocessing. So yeah, we definitely see other material in RIOB.
Thank you, Jeremy. Talita, there is one question for you there. Is there any other test you would recommend to assess the effects of ultraviolet radiation on bitumen aging?
Thank you for your question. Yes, I think it will be interesting to complement the rheological results with a chemical test. So I would recommend infrared spectroscopy, FTIR, because through this test, it's possible to observe the increase of carbonyls and sulfoxide functional groups, which are representative of the bitumen aging, and then evaluate the effects of ultraviolet radiation on the samples.
Thank you. And another question for you, Talita. What is the percentage of rubber you used in the bitumen, and what was the binder type that you were using in your?
And we use it basic binder 5070, PG 64, and the percentage of rubber, it was 13%. And then the sample with rubber and PPA, we got 11% of rubber and 0.5% of PPA.
Thank you. Yeah, I will ask a question to Jeremy now. You have assessed the bitumen oxidation, so using SARA AD with infrared spectroscopy. Did you observe similar trends, whatever the bitumen origins? And what I mean there is different streams or refining processes. And the other question I have for you was, so SARA AD tool to address the composition of bitumen or neat binder. What's about using the SARA AD for PMBs?
Okay, so yeah, so we have used the SARA AD, if I understand the two questions well, to evaluate oxidation of different binders from different origins and different processing conditions. So we do see that certain binders from certain reservoirs and geological formations are more sensitive towards oxidation. So they do build up more carbonyl plus sulfoxide species, and they do produce more asphaltenes, more of them and more quickly than other sources. And interestingly, when we look at, so we have an asphalt industry research consortium where we've looked at many binders from around the world, and there are huge differences, and especially a lot of the refining practices in Europe, for whatever reason, do actually show lower amount of asphaltene buildup and lower amount of carbonyl plus sulfoxide. On the processing side, if we look at visbroken residues, they also tend to oxidize more quickly than other residues that haven't been thermally cracked. And as far as additives like polymer modified bitumen, we can see some of the additives in the method, and we see that, for instance, SBS polymer shows up in kind of the resins, but in the cyclohexane soluble asphaltenes. But we've added size exclusion chromatography, and so we can actually separate out with the size exclusion chromatography the polymer peak. And with our wax faultine determinator separation, we can see other additives like Sasobit and also EVA polymers will show up more in the crystallizable wax fractions in that separation. So Sarah AD doesn't capture everything for all the different additives, but using a combination of other tools, we can see those other additives.
Thank you, Jeremy. I will ask the last question to Talita. From experience, we know that the UV aging equipment can only reach to limited depth of the sample in terms of micrometers. Have you looked into that? I presume that the samples obtained after UV aging are homogenized together before testing. Is it correct?
Yes, and this is a limitation of the research, because forgetting the amount of material that we needed to perform in the rheological test, we needed to use it around 30 grams, and in our calculation, we get about 0.43 millimeters in our UV aging procedure. So we homogenized the sample together, consider everything that was aged in the widerometer.
Thank you, Talita. I'm just looking at my watch, and I believe that I will need to close the session. So first of all, I would like to thank a lot our 6 speakers for their presentations, the preparation, and their active contribution to the live Q&A parts. I would like also to apologize because I might have missed some questions in the Slido due to the time constraints, and it was not easy to go through all the list. However, there is this specific chat opened in the networking lounge with the name of our session. So 2B, session 2B, binder performance and testing. So everybody, every attendee can keep discussing matters of this session in the chat. So I do encourage all of you to use this channel in case you would like to pursue discussion with the speakers. So many thanks for your participation. I hope it went smoothly and you have enjoyed this first session. And I wish you all a good continuation with the other sessions of the Congress. So hope to see you, all of you, in the next sessions. Thank you very much.
Thank you.